Meteorite strikes on Earth may create unexpected form of silica. When a meteorite hurls through the atmosphere and crashes to Earth, how does its violent impact alter the minerals found on a landing site? When can the short-lived chemical phases created by these extreme impacts teach scientists about the minerals existing at the highest temperatures and pressure conditions found deep inside the planet? New work led Carnegie's Sally June Tracy examined the crystal structure of the silica mineral quartz under shock compression and is challenging long-standing assumptions about how this ubiquitous mineral behaves under such intense conditions. Quartz is one of the most abundant minerals in Earth's crust, found in a multitude of different rock types, Tracy explained. In the lab, we can mimic a meteorite impact and see what happens. These results are published in Science Advances. Tracy and her colleagues in Washington State University, WSU, Stephen Truner, and Princeton University Thomas Duffy, a former Carnegie Fellow, used a specialized cannon-like gas gun to accelerate projectiles into quartz samples at extremely high speeds, several times faster than a bullet fired from a rifle. Special X-ray instruments were used to discern the crystal structures of the mineral that forms less than 1/millionth of a second after impact. Experiments were carried out at the Dynamic Compression Sector, DCS, which is operated by WSU and located at the Advanced Photon Source, Agroni National Laboratory. Quartz is made up of one silicon atom and two oxygen atoms arranged in a tetrahedral lattice structure. Because these elements are also common in the silicate-rich mantle of the Earth, discovering the changes quartz undergoes at high pressure and temperature conditions, like those found in Earth's interior, could also reveal details about the planet's geologic history. When a mineral is subjected to extreme pressure and temperatures, its internal atomic structure can be reshaped, causing its properties to shift. For example, both graphite and diamond are made from carbon. But graphite, which forms at low pressure, is soft and opaque. A diamond, which forms at high pressure, is super hard and transparent. The different arrangements of carbon atoms determine their structure and their properties, and that in turn affects how we engage with and use them. Despite decades of research, there has been a long-standing debate in the scientific community about what form silica would take during an impact event or under dynamic compression conditions such as those deployed by Tracy and her collaborators. Under shock-loaded silica is often assumed to transform to a dense crystalline form known as stashovite, a structure believed to exist in the deep earth. Others have argued that because of the fast timescales of shock, the material will instead adopt a dense, glassy structure. Tracy and her team were able to demonstrate that counter to expectations, when subjected to a dynamic shock of greater than 300,000 times normal atmospheric pressure, quartz undergoes a transition to a novel, disordered crystalline phase whose structure is intermediate between fully crystalline stishovite and fully disordered glass. However, the new structure cannot last once the burst of intense pressure has subsided. Dynamic compression experiments allow us to put this long-standing debate to bed, Tracy concluded. What more impact events are an important part to understanding planetary formation and evolution, and continued investigation can reveal new information about these processes.